Okay, so some of this we already did in class, but let's go ahead and go through the whole section together here for the notes. So the fundamental theorem of calculus, again, basically just says that the integral and the derivative are inverse operations. So if I find the integral from a to x of f of t dt, and then I take the derivative, I basically get back to where I started. So first, let's understand what this function is saying right here. So what you can think of is if f is the function whose graph is shown to the right, and g of x is the integral from 0 to x, we're going to find g of 0 through g of 5, then sketch a rough graph of g. Okay, so what we're trying to do is 0 to x tells me the area from 0 to x. So when g of 0, the area from 0 to 0, well, that's going to be 0. Now 0 to 1, so we're going to figure out the area of this triangle here. So that triangle, notice it has height 2 width 1. So g of 1, this area is going to be 1/2 times base times height, which is equal to 1. So g of 1 is equal to 1. G of 2. Well, notice that basically we got to have this rectangle and we got to have this triangle then, because we're going from 0 to 2. So this area of that rectangle is 2, area of the triangle is 1, so 2 plus 1 gives me 3. Now, g of 3, we got to figure out approximate area of this guy right here. So let's just call it, it's a little bit bigger than 1, let's call it 1.3. So the area there is 1.3, so add them all up, I get 4.3. G of 4, well, this and this look like they're the same, but this one's below the x-axis, so let's call that area negative 1.3. So we're going to be back to 3. And finally, g of 5, well, this looks like another negative 1.3, so let's take another 1.3 away from that 3, and I get about 1.7. If I basically add all those numbers up. And that's number 1. The nice thing is these are pretty easy once we see how to do them. So find the derivative of the function g of x equals 0 to x of square root of 1 plus t squared dt. Basically, since they're inverse operations, what ends up happening is we basically take this guy and plug it in down there. So the derivative of that, g prime of x, is going to equal square root of 1 plus x squared. And we're done. Example 3. Find the derivative of the function g prime of x. Well, this one's a little bit different. We're going to plug in x squared. So I get x squared squared. But our answer is not just, let me leave a little extra spacer. Our answer is not just 1 plus x to the 4th. And the reason for that is when we differentiate, we plugged in x squared, so when we differentiate, we're going to have to use the chain rule. So when we differentiate, we get this extra 2x, because the derivative of x squared is 2x. And so I end up with 2x square root of 1 plus x squared, and that ends up being our derivative. So the short answer is, take this guy, plug it in for the variable, in this case t, and then multiply times the derivative of that guy. The fundamental theorem of calculus part 2 basically says that to find the area under the curve, I can find the antiderivative, plug in the top number, plug in the bottom number, subtract 2, and we've got our answer. So, example 4, evaluate the integral. So how we're going to do this, we're going to say, well, the antiderivative of x squared is x cubed over 3. And what we do is we write a line there to indicate that we've already found the integral, but we still need to plug in 2 and 4. So I'm going to plug in 4, and plug in 2, and subtract the 2. So 4 times 4 times 4 is 64 over 3, minus 8 over 3 gets me 56 thirds. Let me write that a little bit neater here. So on this one, again, first thing we have to do, calculate the antiderivative of e to the x. Well, what's the antiderivative of e to the x? It's e to the x. Now, we don't have to worry about the plus c on definite integrals like this, because when we subtract, the c's will cancel. So we just, e to the x from 3 to 6, so I get e to the 6 minus e to the third. You could find a decimal approximation, but leaving it like this is fine. All right, find the area under the curve y equals 3x squared from x equals 0 to x equals 2. Again, that's just basically another way of saying we want to go from 0 to 2 of 3x squared dx. The antiderivative of that is x cubed. We're doing it from 0 to 2. So you get 2 to the third minus 0 to the third, which is equal to 8. All right, now we get a little bit more interesting. If we look at this, the integral from 0 to 4 of this guy, as it is, we cannot take the antiderivative of each part. Things that are multiplied, we can't really deal with that. However, if we multiply that square root of t through, we can write this as 4 root t minus, and t times t to the 1/2 is t to the 3/2. You can write it this way. And one thing that's useful here then is the square root of t is the same as t to the 1/2. So 4t to the 1/2 minus t to the 3/2 dt. All right, so now I need to find the antiderivatives. So I'm going to use the same rule that we did before. I'm going to add 1 to the power and divide by it. So it ends up being 4t to the 3/2 divided by 3/2 minus t 3/2 plus 1 is 5/2 divided by 5/2 from 0 to 4. Well, we can rewrite that nicely. Dividing by 3/2 is the same as multiplying by 2/3. So I end up with 4 times 2 gets me 8 t to the 3/2 over 3 minus the same thing here, 2 t to the 5/2 over 5. So now let's go ahead and actually plug it in. So 4, take the root and then the power. So 4 square root of 4 is 2, to the third is 8, times 8 gets me 64/3. Plug in 4, 4 square root of 4 is 2, to the 5th is 32, times 2 gets me 64/5. Now when I plug in 0, 0 to the power is still 0, so I get 0 minus 0. So this is minus 0 minus 0. You don't have to write that part down, but don't forget to subtract the bottom number. So I don't know how we could use our calculator or just find a common denominator. Let's do a common denominator. Multiply this guy top and bottom by 5. So 5 times 64 is 320 over 15. This one top and bottom by 3. So 192 over 15. Subtract, I get 128. That's 128 over 15. And I don't think there's any common factor there. So, no, there isn't. So 128 over 15 is our answer. Last one. Again, this one looks really complicated. What we absolutely cannot do, well, that's b to the third over 3 minus 2b to the 3/2 over 3/2 plus 4b over b squared over 2. I can't just do it piece by piece like that. If we didn't have that division, I could. But they're all divided by b. I cannot just take the antiderivative of each part because of that division. So let's not do that. Instead, what we're going to do here is we can split it up this way. B squared over b minus 2 root b over b plus 4 over b db. And if we simplify that a little bit, b squared over b is just b. Remember, we subtract when we're dividing, so this is b to the 1/2 minus 1. I get minus 2b to the negative 1/2. And then I'm just going to leave that as 4 over b, because that's kind of a special case. If I think of that as 4b to the negative 1, our power rule doesn't work because we'd have 4b to the 0 over 0. So just remember, when it's just a plain old b or a plain old x or whatever variable we're using on the denominator, we're going to have to use, remember the antiderivative of that is the natural log. So now let's find the antiderivatives. The antiderivative of b is b squared over 2. The antiderivative of negative 2b, we're going to add 1 to the negative 1/2, so I'm going to get to the 1/2 divided by 1/2 plus, this is going to be 4 ln of b from 1 to 3. All right, so b squared over 2 minus 4 square root of b plus 4 ln of b. So it's not going to be a super nice answer. So I get 9 over 2 minus 4 square root of 3 plus 4 ln of 3 minus 1/2 minus 4, because square root of 1 is just 4, plus 4 ln of 1. Well, ln of 1 is just 0 as well, so 0. So I end up basically with 9/2 minus 1/2 is kind of nice. That gets me 8/2, so it gets me 4. Minus the negative 4 gets me 8, so I end up with 8 minus 4 root 3 plus 4 ln of 3. And there's my answer.